So let's take a look at that. Just a quick review of those properties. So we had a couple problems where we were going to simplify with and without a calculator. We looked at some logarithmic and exponential functions and how those are related. Just kind of restated some of the ideas that we had before. And then we went over some what I find to be really interesting and useful properties, especially in higher mathematics, of if we've got a logarithm, they've got all these nice properties. So the first thing is, and generally speaking, all of these are going to simplify the operation. Simplify the operation. So addition and subtraction are generally much easier than multiplication and division. Multiplying by a single constant, by a single number, is usually easier than raising something to a power. And that's what each one of these properties does. So this is the product property of logarithms. It allows us to change multiplication into addition. The quotient property, or the division property of logarithms, allows us to change division into subtraction. And the power property, which is really cool, allows us to take this exponent that's up here and move it out in front and use it as a multiple. So it allows us to change powers into multiplication. Okay? Allows us to change powers into multiplication. So we went through and we did a couple of examples of each one of those. We did 2 examples of each one where we're applying the property in this direction, where we're simplifying the operation, and here where we're taking this property and putting those together. So we're writing one single logarithm, granted with a more complicated operation. In this case, it's multiplication, but in the end, it's simplified. It's one single logarithm. And I mentioned yesterday that on a lot of the homework assignment, you're going to look at that and go, there's not really an answer to this. Okay, and all you're doing here for the most part is you're practicing using those properties. You're practicing applying those ideas. Okay, so you're going to get expressions that are answers, not necessarily a simplified answer. So on this problem right here, we're not looking for what power we put on a 10 to make a 36. That's not the point. The point is that I can take log 4 plus log 9, write it as log of 4 times 9, or simplify that to be the log of 36. Okay? By the way, just as kind of an emphasis, if you put that in your calculator and got a decimal, that's less exact than leaving it like this, because this is the exact answer, log of 36. Okay? So you do have to get used to the fact that when you see, log of 19 or whatever it happens to be, that's just a number. It's just a number. You can use it like you can any other number. Yeah.
I was just going to say, so would we, if it's like that, log 4 plus log 9, instead of having the times them together, can we just put in our calculator log 4 plus log 9?
If it said what number does this equal, yeah. Okay. If it said simplify using the properties of logarithms, that right there is the correct answer. They wouldn't want you to put it in a calculator either way. Okay. Either way, this is more exact than typing it into your calculator. Okay. And it demonstrates that you understand the properties of logarithms. Okay. Anything else? Okay, we went over those 3 properties, all of which were new. Of course, we emphasized the fact that logarithms and exponentials of the same base are inverses of each other. They undo each other. Okay, and then we reminded ourselves of these 2 properties right here, that if I have the log base b of b, it's 1. If I have the log base b, so any base you want of 1, it's got to be 0. Okay, and then just a quick reminder. So a quick problem right here. Given that f of x is b to the x, or in other words, the name of that function would be, what is it? Exponential base b. What would its inverse be? Its inverse would be log base b. So log base b of x. Those 2 should be inverses of each other, and we can check that by doing f of f inverse. So if I do f of f inverse, what got plugged into what here? The inverse into the original function. So the logarithm into the exponential. So that would be b to the log base b of x. What do you get? You get x, just like you'd expect if they truly are inverses. And if I do f inverse of f, what got plugged into what here? The other way. The exponential got plugged into the logarithm. So this would be log base b of b to the x, and we get x. Again, Very abstractly, okay, we're just showing in general that if you have logarithms and exponentials of the same base, they are inverses of each other, so they do undo each other. Okay, are there any questions there? So those are inverses. Okay, sure? Okay. You remember there are two logarithms that we've got on our calculator. What are they again? Okay, you've got ln, the natural log, and log base 10, or just the common log. So those two are on your calculator. So you can find log base e and you can find log base 10. Type it into your calculator, you're done. But remember, we had a starter question problem, this one right here. It was the log base 3 of 4. 3 to what power gives you a 4? And we kind of narrowed that down that it would be in between 1 and 2, closer to 1 than it is to 2. But if you have to find something like that and get a decimal approximation, again, like I mentioned the other day, you're stuck looking it up in a logarithm table. Good luck if any of you have one. I don't even have one. Okay, you could probably find one on the internet. But we've got these fancy tools that know how to find logarithms, especially common log and natural logarithms, but they don't have this in there. Okay? So, yeah.
What exactly does log stand for? Like, how did they ever figure out log base 3 and 4?
Okay, so
Put it in the calculator.
okay, so if you don't want to listen to this discussion, then so why did they use log?
Yeah, what does log mean?
Okay, I'm not sure why they used the word logarithm. Okay, it's probably just by definition. There's probably some reason for that somewhere back in history, but they could have used any word that they wanted to. It's like, why did they come up with the square root symbol or the radical symbol to represent roots? Well, they just did. They could have come up with some, maybe they should have made it a squiggly line and then a straight line on the top or something like that. But it's basically the notation for the radical. It just means that's a root. If we put a 2 in the little crook there, it means the square root. If we put a 7, we want the 7th root. And it would mean, what number do you multiply it by itself 7 times to get the number underneath there? Okay? When we write something like this, all this is just notation that helps us ask the question. 3 raised to what power gives us this number right here? Now, how would they produce a logarithm table that has all those answers in it without using a calculator? Lots of fancy techniques, and if nothing else, you know it's in between 1 and 2, so maybe try 1.1. Maybe it's between 1.1 and 1.2, so you do 1.15 and maybe 1.6 or something like that, and you keep narrowing down. Yeah, it would take a long time, okay? They also have slide rules and stuff like that that none of you are probably interested in learning how to use, but lots of ways they could figure that out, okay? I heard some nopes. That's very nice. Any questions? Okay. All right. So how do we find this? Well, we find this, we turn this, basically what we do is we use properties of logs to turn this into something, into a base that we can actually use. So this is called the change of base formula, okay? The change of base formula. And what it says is if I have the log base A of m, I can find the log base B of m, put that on the top, and the log base B of A and put that on the bottom. So what I kind of envision these kind of making a counterclockwise turn, okay? So I see the A floating down toward the bottom and the M kind of coming straight across. So this one's over here and that one's right there. What this allows us to do is change this to any base we want. Now, if we're going to use our calculator, there are only 2 bases that really make sense. So what I'd probably do is do the ln of M over the ln of A, or I could do the log of M over the log of A. Now, what I can't do is I can't do this. I can't do the log of M and put it over the ln of A, okay? That's not okay. You can't do that. It has to be the same base logarithm on the top and on the bottom, okay?
So how do you do, but log is 10 and ln is e, so how can you just go from an e to a 10 or 10 to e?
Well, okay, you don't focus on these two. Look at this one for the time being.
Log an equals to ln.
This is the rule right here. It says as long as you're changing it so you've got the same base on the top and bottom, you can put the m on the top, take the log base b of m, and the a on the bottom, take the log base b of a, and that will give you the same answer as if you had this right here. So what it does is it changes it into something that we can do with any base, or specifically these two examples right here. These we can find on our calculator. Okay, so let's go through and do a couple of examples and see if this doesn't make sense. So on this problem right here, this is what we do. So grab your calculator. And if you're interested in this, in a proof as to why it works the way it does, I'd be happy to play around and we'll take a look at it. Okay? Oh, thank you. Your enthusiasm is completely overwhelming. So if we were doing this problem, we've got two choices to plug this into the calculator. So I could do the ln of 4 over the ln of 3. And I think I already told you, I'm biased toward ln. I like ln. It's one fewer letter and it's funner to say. Okay? So if I were to type that into the calculator, this is what it would look like. So if I want to know what log base 3 of 4 is, I'm going to do the ln of 4. I've got to close the parentheses, and then I've got to divide that by the ln of 3. You don't have to close the parentheses. That closed parens would be implied there. But if I hit enter, there's the answer. Remember we said it was going to be between 1 and 2, closer to 1 than it is to 2. Now, if you think, my gosh, that's magic and I don't buy that, remember, that's the answer to this logarithm. The answer to a logarithm is an exponent. An exponent that goes on what base? For this one right here, 3. So we should have 3 to the 1.26 should be approximately 4. So if you want to check this, and you don't need a fancy calculator like an 83 or an 84 to get this, you can do this on those regular TIs. Okay? If I did 3 and then I raise that to the last answer, it's going to give me exactly 4. So that is the right answer. Okay? I could also do this if I wanted to. So I could do, well, let's do the common log, because that's on our calculator also. Let's do the log of 4 over the log of 3. So the cool part about this is I can just recall this. Okay? On your calculator, if you've got a 34 or something like that, you can just hit the up arrow. Okay? So I'm going to change that to a common log. I'm going to change that to a common log. So now I have log base 10 of 4 over log base 10 of 3 because they're the same base. This is going to give me exactly the same answer. Okay? So that's definitely right. So is everybody convinced that that does indeed work? Mm-hmm. Okay, questions? Yeah.
So, I know you probably answered this billions of times, but how many decimal places should we round?
Usually at least 3. Usually 3 is enough. If it tells you more than that, then you'd want to do more than that.
Not said.
Yeah. Okay. Any questions? Okay, let me just show you, just for the sake of argument, you cannot do this. This does not work. You can't mix a different base on the top with a base on the bottom. Okay, that's not okay. If I hit enter here, it's going to give us something other than the correct answer. Okay, so please don't mix those up. Same base on the top and bottom. ln on top, ln on bottom, common log on top, common log on bottom. Any questions there? Okay, so you can even do some really weird problems that seem totally bizarre. Log base pi of 10. 10 to what power gives us, or sorry, pi to what power gives us 10? Now, 3.14, it's about what pi is. So roughly the answer is going to be around 2. So if I were to do this on the calculator, I'd just type in ln of 10 divided by the ln of, divided by the ln of pi. So that's right here. I'd hit enter and there's the answer. So a little more than 2, about what we expect. Okay, so this is the ln of 10 over the ln of pi. Or let's stop and think about this for just a second, because this actually is kind of cool that you've got properties of logs here. If I did the common log of the top over the common log of the bottom, do you know one of these? Yeah, this is log base 10, this is exponential base 10. What's the exponent? A 1. So you've got 1 over the log of pi. So if you type that into the calculator, that'll give you the correct answer also. Or if you were to say, hey, can I write this as simply as possible? That's maybe about as simple as it gets. At least it's in terms of a logarithm that we're mostly familiar with. Okay? Log base 10 is a heck of a lot more familiar, or maybe easier to understand than log base pi. Questions there? Okay. Oh, and I didn't fill this one in. They're on our calculator. That's why we like to use those. Roughly, what would the answer be here? On this one?
Oh, that 4.087.
Yeah, we're expecting it to be a little bit bigger than 4, right? Because 2 to the 4th would be 16. So what did you say it was?
4.087.
087. Okay? And again, if you're not sure, there's no excuse. Type it into your calculator the other way. This is the answer to a logarithm. It's the exponent that goes on 2. So do 2 to the 4.087. It better give you something really close to 17. Questions there? Yeah.
So on our homework, is it going to say write an exact form or decimal approximation?
Yeah.
It'll say.
Yep. Okay. And again, like I mentioned before, how can you check your answers here? Again, take the base, raise it to the answer to the logarithm. That's an exponent, and it should equal out. Okay. Please make sure, okay, so this goes to what Zach was talking about right here. Please make sure that when you're doing the problems, look at the instructions and read them carefully. Okay? For what looks like the same problem, if they give you a different set of instructions, one might say, write it in exact form. The next one might say, get a decimal approximation on your calculator. Some might say, use the properties of logs to write them as separate logarithms, a sum and difference of logs with the powers written as multiples or factors. Okay, and then others might say, write as a single logarithm, and that's what we're going to practice now. So it says, use the property of logs to find the exact value of the expression without using a calculator. Notice what it says there. Find the exact value. Okay? And don't use a calculator. So let's follow the instructions. On this problem right here, log base 7 of 7 to the 31st. Do you have problems like that? Answer? 31. End of story, we're finished. It's literally that quick. Log base 2 of 60. Not quite sure what that is. I don't know what 2 to what power equals 60 is. Minus the log base 2 of 15. But using the properties of logarithms, I have two separate logarithms. They are both base 2. If they're both base 2, I can write this as one single logarithm. And logarithms allow me to work backwards and change subtraction into division. So this would be 60 over 15, which is log base 2 of 4, which is now a number I can calculate, and it's 2. Answer to that one's 2. Now, stop and think for just a second. This isn't very impressive to people in this class. If you were to show me, hey, you showed me how to do this and now I can do it. All right, that's great. You learned what I taught you. But if you go show anybody else, go home and show your parents, you know what? Do you have any idea what this means? They'll have no idea what you're talking about unless they're engineers or mathematicians or physicists or something like that. And you'll say, you know what? I can tell you, think about what we just did. 2 to what power equals 60? Don't know. And neither will your parents. 2 to what power equals 15? Don't know. We could estimate that this is about 6, a little less than 6. This is a little bit less than 4. And yet, using the properties of logarithms, we know the answer is exactly 2. Okay? Pretty cool that you can keep track of all that stuff in your head. What about this one right here? No idea what either number is, but I can use the property of logarithms to write this as log base 6 of 36. You could still show that to your parents. They won't know what it is. But you know 6 to what power? 2. Answer there is 2 also. Okay? What about this one right here? This one's kind of interesting. Looks really, really awful. That looks ridiculously complicated. What can you do with the stuff in the exponent? Yeah, put those together. Let's write this as the log base 5 of 9. Logarithms change subtraction into division. The one with the negative in front of it is going to go on the bottom, so that would be 9 over 3, so that's going to be 3. And the answer here is 3. Okay? All using properties of logs. The fact that those are inverses of each other, or the fact that we can use logarithms to change addition into multiplication, division into subtraction, vice versa. Okay? Any questions? Okay. Again, a lot of these, they're just asking you to do some mental thinking here. How could I apply what I know to solve a problem like this? Look at example number 8. Example 8 says, given that the ln of 2 is equal to a, whatever a is, okay, and the ln of 3 is b, use the properties of logs to write the ln of 3 over 2 in terms of a's and b's. So the only thing we're allowed to have in our answer is numbers, a's, b's, and operations like addition, subtraction, stuff like that. So how can I rewrite this? Let's focus on this for the time being. ln of 3 minus the ln of 2. And what did they say the ln of 3 was? B. And what did they say the ln of 2 was? A. Done. That's it. That's aggravating for some people. They're like, well, that's not an answer. Yeah, it is. It's an answer in terms of the way they asked us to write it. Okay? Just some mental hoop jumping here. Can you apply the properties of logarithms to do exactly what they asked you to do? Any questions there? Easy enough? Sure there aren't any questions so far? Because this gets a little bit more complicated now. We're good? Okay, so let's take a look at this. This set of instructions for problem, or for example number 9, it says, write each expression as a sum or difference of logs. Write powers as factors. Okay, this is using the properties that we learned on the front side, kind of in the forward direction. Okay, we're going to write this as a sum or difference of logs. We're going to take this and we're going to simplify the operations, not necessarily simplify the expression. So what I'm going to notice is I've got multiplication here and I've got an exponent. So how could I write that multiplication or rewrite it using the properties of logs? Logarithms allow us to change multiplication into addition. So I'm going to write log base 7 of 5 plus log base 7 of y to the third. Now you'll notice that the 3, the exponent was over the y, not over the 5. That's why we can separate that completely. Okay? Now, should I do anything else according to the instructions? It says write powers as factors or as multiples. So I'm going to take this and I'm going to slide that out front. Now, if I can see that and do it all in one step, we're going to write it here. Actually, let me just write this way. That way it'll be clear what the work is. That's the answer. Seems weird that we've got this ugly expression here, but that's the answer. Okay? I knew you wouldn't. Okay. Any questions there? Okay, let's look at the next one. Got some powers here, got some division, got some multiplication. Any ideas? There is going to be a minus in there. How many terms are we going to break this into?
3.
Actually, we're going to do 3 here, okay? And if you keep in mind what I said, anything in the denominator, anything we're dividing by, what's it going to have in front of it? It's going to have a negative. So this is going to be log base. Now leave a little bit of space here, and if you're writing in pen, be a little careful. Pencil, you're okay, right? Kind of light. Okay? This is going to be x plus 3 raised to the 5th. Now, that's on the top. It's going to be positive. These are on the bottom. Oh, it is you. Thanks. You. Nope. Nope. Okay? This one's on the bottom, so I'm going to make that negative. So that's going to be the log of v squared. This one's on the bottom. It's going to be negative, so that's going to be the log of w minus 4 raised to the 6th. So I've got a factor on the top, 2 factors on the bottom. That's going to give me 3 terms altogether. The ones that are on the bottom have negatives in front of them. And the only thing I have left to do on this problem is do what? Move the exponents, move the powers, and make those factors, right? So I'm going to slide this out in front. I'm going to slide this out in front. And I'm going to slide this out in front. And there's the answer. Okay, now we know Tylin doesn't like this. Does anybody else have a problem with this? Any questions? What's that? Okay, apparently Marissa doesn't like this either. Okay, any? That's great. There are probably other people that don't like it, but that's the way it is. They haven't said anything yet. What's that? So? Okay. Any questions?
No, please.
Okay, I just want you to watch. Okay, don't write this down. I just want you to watch. Is this okay? Oops, that's a 3. Is that okay? Negative exponent. If I take this and move it on the top, what happens to the exponent? Doesn't it change signs?
Yes, it's also flipped, so it's negative. Oh, didn't pop up. I'm losing it.
I've got the log outside, and all I did is I moved this onto the top and changed the sign of the exponent. Moved that on the top and changed the sign of the exponent. Is that okay?
Yeah.
Okay, do I have any division in here anymore? Nope. So none of them are on the bottom, right? So this is going to be log of u plus 3 raised to the 5th plus log of v to the negative 2 plus log of w minus 4 raised to the negative 6, right? What do I do with this? Move it out in front. That's a 5, right? Move it out in front. Negative 2 in front. Move it out in front, negative 6 in front. Do you see why the ones on the bottom have a negative in front of them? Because if they're in the denominator, what type of exponent do they have? They've got a negative exponent. That's why it changes division into subtraction. Does that make sense? Now, I wouldn't recommend doing this. It's a heck of a lot faster to do this, that idea that I just told you about. Okay, if they're in the denominator, they've got a negative in front. Okay, if they're in the numerator, they stay positive. Got it? Okay, all right. But that's the idea behind it. Let's take a look at, slide this back over here. Let's look at this one. Okay, now you'll remember a couple days ago I said logarithms don't play very well with radicals. Logarithms don't play very well with radicals. They work really well with exponents. So what do you notice that we could do with this to make it a little bit easier to work with logarithms? Yeah. Change the radical into an exponent. This is a square root, so what exponent is that? That is to the 1/2 power. So this would be log base 3 of x squared, and then this would be y minus 1
5/2.
to the 5/2. Okay, that's it. Do I have any division? Nope. Okay, so for the time being, I'm going to write down log base 3 of x squared plus log base 3 of y minus 1 raised to the 5/2. And what am I going to do with that power and that power? Slide them out front. Now, if you can do this all at once, that's totally fine with me. But that right there, as much as it bugs all of you, that's the answer. Any questions? We sure? Okay, let's look at this last example right here, and then we'll go on to the other type. Now, with a little bit of practice, you can look at that, and then you can just write down, let's see, how many terms would I have? 3, because I've got 3 factors. I've got 2 factors on the top, and I've got 1 factor on the bottom. So I'm going to have 3 different terms. How many are going to be positive? 2 of them, because they're on the top, and only 1 of them is going to be negative. I've got some radicals here, so I've got some fractional exponents. So I'm going to have some fractions sitting out front. So if I were to break this into the 3 pieces, this would be log base 4 of x squared plus log base 4 of, I'm going to write this as 2x plus 7 raised to the 1/2. And then this is going to be minus log base 4 of 5x minus 6, and that's going to be raised to the 1/3. If you can do that in your head and slide the exponents out front, then you're in business. So this would be 2 log base 4 of x plus 1/2 log base 4 of 2x plus 7 minus 1/3 log base 4 of 5x minus 6. And that right there is the answer. Any questions? Got it? My apologies. I can guarantee you there are times where it is much more useful to work with this than it is to work with this. Okay? Calculus would be one example. Okay? All right, so let's take a look at example 10 and then we'll go on. Now, what we've done right here is we've kind of used those properties in the forward direction. I want to point out something right here that is a very common misperception, misunderstanding about how logarithms work. Is the log of x plus y equal to the log of x plus the log of y?
No.
It is not. There are very few functions that distribute. Very few functions distribute. Almost none. Multiplication will distribute. But even things like this. Does that distribute? Can you do the square root of 25 plus the square root of 9 and get the right answer? No, because that would be 5 plus 3. That's going to be 8. This number's only 34, so it's a little less than 6. There's no way that works. This doesn't work, and the answer here is that is false. These two are definitely not equal. Please don't try and distribute the logarithm through. It does not work that way. It would be great if it did, but it doesn't. It will be completely wrong. Okay?
But we could just add xy and then do the log base b of whatever number that is.
Sure. Yeah. Follow the order of operations. Do the parentheses first if you wanted to think of it that way. Okay. Any questions there? Okay. Take a look at example 11. The instructions are pretty simple. It says write each expression as a single logarithm. You might like this better than you like the other one because we're used to simplifying things. Those other problems, it looked like we were making a mess out of it. Here, we're putting these together as one single logarithm. So those steps that we took before, you basically do these in reverse. So I'm going to take that expression right there, and the first thing I'm going to do is I'm going to write the ln of u squared plus the ln of v to the 1/2. Put the powers up there. Notice that this is addition, so I can write the ln of u squared times v to the 1/2. And then if I wanted to put it into something that I could maybe compute or understand how to compute, that would be the ln of u squared plus the square root of v. And that right there is the answer. If that works better for you and you like that better, that's fine. But using these properties in both directions, both are really important skills. Any questions?
Plus square root of v or just
This right here, it's just times. Yep, multiplication there. Because we're changing the addition back into multiplication, if you want to think of it that way. Okay, let's take a look at this one right here while we're at it. Okay, on this problem right here, notice that they're both log base 2's. Okay, I do a couple of things to kind of clean this up. So this is going to be the log base 2 of x to the 3/2 minus the log base 2 of, might not be a bad idea to write it like this. Is that okay? Now, I'm going to show you two different ways to finish this off. Okay? So this is division, right?
yeah.
Okay? So I'm going to write the log base 2 of x to the 3/2 goes on the top, x to the negative 1/2 goes on the bottom. You with me there? But that's ugly. I'm going to take this and I'm going to move it up on the top. So this is going to be the log base 2 of x to the, well, that would be 3/2 times x to the first. And if I'm multiplying those, what do I do with the exponents? You add them together. So this is the log base 2 of x to the 5/2.
Okay, now when you move the log base 2x to the negative 1, wouldn't that x turn positive?
No. We put it underneath there because of the properties of logarithms, not because of the properties of exponents. Not because that means reciprocal. Yeah.
Why did you times the logs together when it was division, which is subtraction? The last one?
You mean right here?
Yeah.
Okay, because what I did is I moved this up on the top. Properties of exponents. Negative in the exponent means reciprocal. The reciprocal of 1 over x or reciprocal of x is 1 over x. So when you move it on the top, it would be x to the first. It changes the sign of the exponent,
Oh, yeah. Okay.
right? You with me there? There's the answer. Would you like to see a little bit easier way to do the same problem?
Sure.
Okay, again, this is the nice thing about properties of logarithms. There are lots of different avenues that you can use to get to the answer. So knowing all of those avenues may make a particular problem easier to do. What if I took this and split it out front? This becomes log base 2 of x to the 3 halves plus log base 2 of x. Logarithms allow us to change addition into multiplication. So this would be the log base 2 of x to the 3 halves times x to the first, right? If I'm multiplying these together and they have the same base, I add the exponents. So this is log base 2 of x to the 5 halves. Now, I would say for the most part, getting into the last chapter, we started hitting some difficult stuff. This is some pretty brainy material here. This takes a while to kind of sink in, figure out how all these properties work. So please make sure you're practicing enough. Okay, are there any questions there? Okay, let's take a look at these two. Let's look at example B first. Again, it says express as a single logarithm. So the first thing we're going to do is we're going to get rid of those coefficients. So I'm going to bring that up there, this up here, and this up here. So I'm going to write log base 6 of x to the 4th plus log base 6 of y to the 1/3. I'm going to leave the minus right here, and this is going to be log base 6 of z to the 5th. And because they're all single logarithms using the same base, I'm going to write log base 6 and use that property in reverse. Anything with a positive, where does it go? On the top. Anything with a negative? On the bottom. So what goes on the top? X to the 4th, y to the 1/3, and on the bottom, z to the 5th. Now, if you want to change that into a cube root, go right ahead. Okay, and just because I'm noticing we need some practice working with the properties of exponents, everybody watch please. If I made this a plus and that a minus, so I moved the -5 up there, so that's a plus, the -5 is now up there. You with me? All of these are positive, so that means that this would be log base 6 of x to the 4th, y to the 1/3, and this would be z to the -5. Do we like negative exponents? Generally not. We usually don't like leaving an answer with a negative exponent. So I can change the sign of the exponent by moving it from the top down to the bottom. So then it becomes this right here. Do you see how there's more than one way to get to the correct answer? Okay. And now let's look at this one right here. Notice where the 3 is. It's on the outside of both of those, right? So that means if we moved it up, it would have to go on both of those, but let me show you how. 3 log of 1 over x plus 3 log of x minus 6 minus 5 log of x minus 6. Again, there's more than one way to get to the correct answer, but take a good look here. I'm going to move the 3 up here. So this is going to be log of 1 over x raised to the 3rd. Now, please take a good look at that. This doesn't always happen. What do you notice about the two of these? They are, what phrase would we use to describe them? They are what type of terms? They're like terms. I've got 3 of them minus 5 of them. So how many do I have? Minus 2 of them. So this would be minus 2 log of x minus 6. Good there? And then you can finish this off a couple of different ways. I'm going to write this as the log of 1 over x cubed plus the log of x minus 6 to the negative 2. Log of 1 over x cubed times x minus 6 to the negative 2. Do we leave it this way? There's our single logarithm, but do we leave it that way? We're going to change the sign of that exponent by moving it down. So this is going to be the log of 1 over, whoops, that should be a 3. Sorry about that. Okay. X to the third, x minus 6 squared. And that right there is the answer. Does that look okay? Any questions? We're good? Okay. Then let's take a look at the last problem. You have some problems like this. They're toward the end of the assignment. It says, given that ln of y equals 2 ln x minus ln x plus 1 plus ln of c, express y as a function of x. Express y as a function of x, and then it says treat c as a positive constant. Could you divide by ln?
Just take that out. Just pretend it's not there.
Okay. If you live in Southwick world, then you could do that. If you don't, you're in trouble. Okay. Okay. When it says express y as a function of x, can somebody give me another phrase that would describe what they're asking us to do? Solve for y. That's what they're asking us to do. Get y on one side all by itself. Okay? Now, I need to get rid of the logarithm in front of y. In order to get rid of the logarithm in front of y, I'd have to raise that side to the e, or get it in a format where I can change from logarithmic form to exponential form. In order to do that, I need to write this side as one single logarithm. So this side is the ln of y. If I write that side as a single logarithm, it's kind of like solving a logarithmic equation, right? Both sides as one single logarithm. Okay? This is going to be x squared. What am I going to do with the x plus 1? Where am I going to put it? I'm going to put it on the bottom. So that's going to be an x plus 1 on the bottom. Where am I going to put the c? I'm going to put it on the top, so times c. So what we've done here is we've used the properties of logs to write both sides as a single logarithm with the same base. And if this says the ln of y equals the ln of this stuff, then what does y equal? Just that stuff, right? So it's going to be c x squared over x plus 1. Have we successfully written y as a function of x? Just a bunch of x's over here? Yep. That's it. End of story. We're done. Okay? Any questions? Okay. Let me just add this, and then I'll give you a few minutes to work on your assignment. For some reason, exponentials and logarithms, okay, and trig functions give people trouble in the long run, okay, because they're new. You're not as familiar with them, okay? I'm teaching my calculus class right now how to find derivatives. You don't need to worry about what that is, but how to find derivatives of functions like this, and they have a really hard time remembering what those derivatives are. And most of the time, it's because they don't understand properties like this, how logarithms work, how exponentials work, how trig functions work, and stuff like that. Now, next semester, you'll get to trig functions. Okay, but for the time being, please put enough work into this that you understand how these work. If you understand these properties and these principles, in the long run, you are going to be much, much better off. Okay? You're going to be the person watching an explanation in the future going, okay, I see what they did there, and not getting hung up on the details. Okay? It's well worth putting the effort in to figure out how these work. Okay? Any questions? Okay, you've got a few minutes to work. If you've got questions, I'd be happy to take them.